I found something really interesting. So I was thinking if I could share, that would be wonderful. Yeah. So actually, this video I want to combine everything about continuous time Fourier series, continuous time Fourier transform, discrete time Fourier series, and discrete time Fourier transform all together. So yeah, I'm going to start with the discussion of something called the duality. So you know that the duality principle applies between my time and frequency spectrum, and so this duality is this one of the duality that is really important to understand connect all the things together is called periodicalization. I don't know how to spell it. Periodicalization and discretization. Its converse also is true, is saying if there is a periodicalization, then it will be continuous. So if you have, pretty much saying, if you have a periodicity in one of the spectrum, on the other spectrum it will be discretized. So I want to talk about the intuition from here to here, and then here to here. So we sort of know that, for instance, say that you have a Fourier basis that sort of looks like e to the j omega t. So that's the standard Fourier so the same for the discrete time, right? It doesn't really matter. So yeah, we sort of understand this Fourier basis, right? And we know that if there's a periodicity of t, then that means the time shift version. So if you say here and then here, so then maybe there is a period. Okay, that's the period, and then that's the period t. So now the periodicity of t, the time shifted version, should have exactly the same frequency response because it's periodic signal. So in that case, we can expand this out into say j omega t, e j omega t, and we sort of scratch that, and then to say that okay, j omega t have to be 1. And we can further solve this by saying wt has to be a 2 pi k, because that has to be wrapped around the circle each time to give us 1, isn't it? So because of that, we can have our frequency to be, so we separate the angular frequency out to be 2 pi k over t. Right. Now I want to discuss something called the spacing. So the thing is that, notice how this is your integer multiples, and then your integer multiples sort of step through saying, okay, this is 0, 1, 2, 3, 4, 5. And sort of set through each one of the step through each one of my frequency. So your frequency spectrum sort of looks like, 2 pi over t, 2 pi 2 over t, 2 pi 3 over t, that sort of thing. So you sort of run through, and then this one is 2 pi 0 over t, that sort of thing. So what's your spacing? So your spacing is pretty much just, your spacing will be 2 pi over t. So this is my spacing. And this is the key point to understand from periodicalization to discretization, is that if there exists a periodicity of t, so if there exists a periodicity of t, then my spacing of 2 pi over t will be some value that is not 0. So there will be some value that is not 0. So in that case, that means there must be a spacing occurs between them. If there is, so I'll repeat that again. So if there is a periodicity, then there must be a spacing between them. So periodicity results in discretization. Yeah, so that's the idea. And let's try to understand its converse. So which is saying, how about a periodicalization results in continuous? And recall that for our continuous Fourier series to continuous time Fourier transform. The key idea is that to extend our periodicity to t to the infinite. So this is a bit of tricky math. So saying, okay, I'm extending from my t equals some periodicity to t equals infinite. So I'm going to run through sort of periodicity of the infinite and then have the scalar function, isn't it? So like, so if you have this infinite t periodicity, then over here your spacing somehow becomes 2 pi over infinite, which is saying the spacing is infinitely small, which is close to 0. So in that case, there's no longer a spacing happening between them, because now my spectrum will be really closely together of each one of my each one of like the spacing will basically be 0. So in that case, it will be a continuous waveform. For my not waveform, sorry, continuous, sort of like a spectrum. Yep. So yeah, so this is the idea of a periodicalization leads to a continuous waveform because there's no spacing anymore. But then how do we actually understand what's the converse of the, like, not converse, but like the, yeah, like, yeah, actually the converse of it, like how to go back from discretization to periodicalization? I actually want to explain this in two ideas. So there's like two methods to interpret this. So the first idea is that for my continuous time Fourier series to discretize discrete time Fourier series, if I were to do that, you maybe have like this, and so on and all that, and then I will have a discretized version by just doing the sampling, isn't it? Well, not exactly the same, but yeah. Okay, that sort of thing. Yeah, so I have a discretized version of this, right? And recall that when we do this, we can actually link the idea to sampling. So when we have the sampling, what happens is that we essentially multiply the whole thing by impulse train. Yeah. So when we do multiplication in one of the spectrum, it does the multiplication in the other spectrum. And something really interesting is that if you have an impulse train on the different spectrum, on the other spectrum, it's also an impulse train. So if you have so if you have given like a sampling time on your frequency response, it also looks like like an impulse train. So in that case, what happens is when you do the sampling here, which is multiplication, it has the convolution here. I don't want to write convolution. So when you have the convolution here, essentially, if you say you've been given, say this is your Fourier spectrum. Sorry, this is your Fourier spectrum, and then it's the frequency response of this one. Although that, yeah, this is the Fourier. It will create infinitely many copies because due to this sampling like the convolution with the impulse train. So in that case, this is coming from, see over here, what essentially I have done is the discretization, right? Because of the sampling. So discretization, sampling, leads to periodicalization. So yeah, that's the sort of like the first way I want to make this to become intuitive is discretization leads to periodicalization. But then how do we actually understand a different thing is that when we this is a bit where I got confused again. What was I supposed to say? What was I supposed to say? I want to explain the idea of so the second way I want to explain this is something called DOF. DOF. So degree of freedom. So the thing is that what is the degree of freedom? So remember how when you have a linear transformation, say you have a I don't know, like a 1 times 5, like already forgot, is it 5 times 1 or 1 times 5? Okay, 5 times 1 I think. So if you have a 5 times 1 and then you do a linear transformation that doesn't have any, so if you have a linear transformation A, and this A doesn't have any, like it's a 4-rank matrix. So in that case, it will be still a 5 times 1, but it's just on a different like sort of basis, right? So we can have, say this is our time and this is actually our Fourier basis. So we can actually choose our different bases. So using this linear transformation to change from one basis to the other different bases. And we'll know that this transformation will be a 4-rank transformation. So we can sort of use that sort of linear transformation sort of analogy to understand the Fourier operators. So in that case, what do I mean by degree of freedom is that so your size of your matrix doesn't change. So essentially what happened was your sort of time information, so all your information, put it into the vector, it will be unchanged. Like the size will be the same for your Fourier. Yeah, so the size should be the same. So what happens is if you have an infinite sort of size, then you should have infinite many information that is still contained in your Fourier as well, in a general sense. And this is the idea where it's a bit strange, is that if we take a look at the synthesis equation, so I'm going to pull out the synthesis equation for my, where is it? So if you take a look at the discrete time Fourier series and the synthesis equation, so the synthesis equation actually looks like xn equal k equal this bit, and then ak ejk 2 pi n over n. Yeah, So the thing is that here we have our k to run through, to sort of run through from like 0 to n minus 1, and then it says that, hey, how come I only need this many? So the thing is that, as you can see, in a period, in a periodicity, if you like sort of zoom out, like zoom in, if you were to say I'm going to put a continuous time into a time vector, this has infinitely many samples. So essentially, my time vector will be like infinitely big. But on the other hand, my time vector for my discretized version will simply contain 5 of them. So in that case, you can see that this change of bases operation, which is the Fourier transformation, the Fourier operator, I mean, sorry, will pretty much contain, so if it's infinite to infinite, so if it's continuous, so we can consider continuous the same as infinite. So if you have the continuous, it will be infinite to infinite. So you can sort of consider now your continuous case will have your spectrum running from negative infinity to infinity, because it has contained sort of infinitely many sort of thing. But then over here in my DTFS case, I only have finite amount of n. So if I have finite amount of n, so if I have finite amount of n samples, then essentially that sort of have like say 0 to n minus 1, that sort of, and you have like that many sorry, you only have that many sort of sample points. But then we sort of combine this with this bit. So the thing is that if you have that many finite amount of points, and then you say, okay, what's the next? So what's the next frequency? So if you have the next period, if you have the next period, you'll repeat exactly the same thing again. And of course, we know that we don't need this information. And then, so the thing is that once you sort of step through this bit, it will be exactly this bit. So, this sort of, the two ideas sort of comes in and then tells you about the idea of repetition, like the repetition, and then, so when you have the repetition actually encodes it's the same thing to talk about the periodicalization, right? So impulse train gives you like periodicalization, make multiple copies, and then also we have only that many bit of degree of freedom. So naturally, what we can see is we'll have a unity circle. So unity circle sort of encodes the idea of like wraparound effect, and the wraparound effect is basically saying, okay, I'm gonna cut one period together, and the next one, it will sort of be on the same roots. So this is the reason why we talk about roots of unity. And then this is the whole reason why you sort of think about, okay, how come in discrete version we will have like a unity circle, like in this form, as you can see. It looks like roots of unity, isn't it? But instead, in a continuous time, it doesn't have this. It will have a linear structure. So this is the linear structure of my frequency response of my continuous time. Meanwhile, if I were to have take a look at this discrete time Fourier series, it will have basically the same linear structure, but then everything sort of contains, the information is all contained within one periodicity, isn't it? And then it will be multiple copies after that. And because of that, you can sort of interchangeably use two different notation to say that, okay, if I were to say this is the start and this is the end, this is like a piece of string. So you just sort of put that piece of string sort of wraps around here, and then, so this is the first piece of string, and then over here I have another piece of string, and then over here I have a third piece of string, that sort of thing. So it sort of wraps around, as you can see. And in that case, you can sort of understand that, okay, for instance, if I have like a spectrum over here, then your spectrum sort of goes like out of the page if you were to like wrap around it into the second axis, and then your spectrum will be the third axis that sort of go out of the page. And that's sort of the fundamental idea about the here, the discretization leads to periodicalization. So I want to encode. I want to explain this sort of intuition about like impulse train that leads to periodicalization from the sampling theorem, isn't it? And then also the fact that you can put this into the roots of unity, sort of like a circle that runs through it. So this is the whole reason why your sort of discrete time Fourier series sort of looks like a roots of unity, and then you sort of look at, oh, okay, it's like, yeah, this is basically the reason of the direct results of my degree of freedom is finite, and the fact that the repetition goes on for my impulse train. Okay, so now we can actually understand every single thing because, wait, have I explained the other bit? Yeah, so again, if you look at the continuous spectrum, there is no periodicity, so it sort of runs through the whole like infinite many, like sort of like negative infinity, infinity. I may sort of actually mixed up the two ideas to get all together here. So if you find any errors, please let me know because I sort of mixed the two together, maybe, perhaps. Okay, oh, okay. So yeah. So what am I supposed to say? Okay, we can actually now try to understand what's going on in. Yeah. Okay. This is the point where I find it's a really good video.
So how are the
so this is by
below the video, where you'll find links to all the other videos.
Oh, that's the good screenshot. So actually, I'm gonna use this as so this is the altogether for the continuous time Fourier, like altogether like CTFT, CTFS, DTFT, DTFS, and LT and GT altogether. Okay, so let's actually take a look at all the characteristic of each one of them. So if you have CTFS, so first of all, let's discuss each one of the cases. CTFT. So I think this is the most highlight of what we just discussed about periodicalization and then also the discretization duality. Okay, so we have discrete continuous Fourier series that's going to be, so what's the nature of this? It will be a periodic signal, and then also it will be infinite, and it will be continuous spectrum, right? Okay, and then for okay, I'm going to show one example first. So this is in my like time spectrum maybe, and this will be my frequency spectrum. So we sort of talk about what's actually going on is that if you have a periodic localization, you will end up with a discretization, discretized, and that's the duality that we discover, isn't it? And then you will have, okay, so the second entry will be infinite. So the infinite means that I have infinitely many sort of degree of freedom. So because it's continuous, so I have infinitely many sort of time axes. So it's not time axes, time vectors, I mean. So in my Fourier basis, it will also be an infinite spectrum. Infinite, yeah, I keep saying infinite like vectors size. Right, so this will also have the infinite degree of freedom. Continuous, so it will be, so continuous leads to aperiodic. Yeah, so the first entry, the third entry will lead to a duality in my frequency response, like as you can see. So this is what we are gonna actually take a look at. So okay, so the same case applies to, okay, so continuous time Fourier transform. So it will be aperiodic, infinite again, and then it will be continuous. So that's the nature of this. And when you apply this, aperiodic will lead to continuous, and then again infinite, and then it will be continuous lead to aperiodic. So discrete time Fourier series will be periodic, infinite, oh sorry, it will be finite n, and it will be discretized. So in that case, periodic means discretized, and discretized means it's periodic, and it will be infinite. Oh, sorry, no, I just copy simply down. No, it's finite. And discrete time Fourier transform will be aperiodic. So because it's a periodic, so we sort of need to run through the whole time axis. So you might still have a finite amount of n, or you might have an infinite amount of n. So that just put infinite. So because you have to go from the whole like time axis you require. So yeah, it's actually infinite, I think. And then it will be discretized because it's a discrete time component. So a periodic leads to continuous, and then this will be infinite. Yeah, infinite. And then I will have discretized lead to periodic. Yeah. So if you were to compare the results from this bit, then as you can see, the first one, the top left one, the CTFS has periodic, and then it will become periodic, so discretized, and then continuous will lead to aperiodic. And the second one, the CTFT, will be aperiodic, aperiodic, so it will be continuous, and then if it's continuous, so it's aperiodic in the frequency spectrum. And the rightmost, DTFS, so you don't really see the CD here because it only run through from, well, actually you can see that. You can see that from negative n to 0, and then to 0 to n. You can see that, first of all, it's periodic. Okay, so from my left side, the time axis, you can see that it's periodic. So on the right hand side, it will be discretized, and my left hand side, it will be discretized. So on the right hand side, it will be periodic. And then for my DTFT, it will be periodic. So on the right hand side, it's continuous, and then left hand side, it's discretized. So on the right hand side, it's it's periodic. So you can see that this sort of concludes everything that we need to know about the duality, isn't it? And let's just finally have a look at the synthesis equation and then the analysis equation for each one of the case of CTFS, CTFT, DTFS, and DTFT. So we sort of remember that for my synthesis equation, so synthesis equation is collecting all my Fourier coefficient. Meanwhile, the analysis is saying I need to sort of get my Fourier coefficient from summarizing all the time information, right? So when we look at this, we actually take a look at, so analysis requires iterating through the whole time spectrum, and an analysis equation requires us to look at one single time information, one single time sample. How do we use all the Fourier bases to construct this? So in that case, we sort of have to look at the opposite way around. So, so for my CTFS, discretized, so it kind of looks like this form, discretized. It's infinite and aperiodic. So in that case, we will have a range of negative infinity to infinity. Yeah, and then, yeah. Okay, that's the first thing. And then for my analysis, it will be continuous. So it will be integral instead of a finite sum. It's infinite, but remember that it's periodic, so we only need to extract one period out of this instead of the whole infinite many range. So we can just require T0. So this is the continuous Fourier series. And continuous. What about the CTFT? So for my CTFT, it will be continuous. So an integral, and an infinite and aperiodic. So you can't simply extract one information out of one period. There's no period. Okay, so continuous, aperiodic. So again, it will be infinity to negative infinity. And then Fourier time. What Fourier time? What is Fourier time? Discrete time Fourier series. Yeah, not Fourier time. What am I talking about? Discretize finite n. So discretize finite n. Yeah, and then over here, discretize finite n. So discretize finite n. And finally, we'll have discrete time Fourier transform. So continuous, infinite, period. So, and then discretize aperiodic, infinite. So I need to run through my infinity. Okay, so that pretty much summarizes everything that we need to know about synthesis equation and analysis equation. And finally, I'm just going to talk about the axes itself. So take a look at the. So recall that now there's a highlight about what's going on happening here. So that, as you can see, this is pretty much what we just discovered. And then, but then the thing is that, look at the continuous sine Fourier series. The axis will be k, and then over here you will have e to the j omega. Like over here, I will use the k omega 0, but in my Fourier transform, it will be w instead, and then like I will use like e to the w, and then I'll have the. So over here, when I use k equals negative infinity to infinity, and then over here I instead use w. Like what's the what's the difference? So recall that previously what we talked about is when we have w t equal 2 pi k because of the periodicity, right? No, no, it doesn't really. Like, yeah, assuming that we have a periodicity, then we have the wt equal 2 pi k, and then we'll have then w equal 2 pi k over t. And recall that we sort of defined in a continuous, in a periodic case, we have like we can have the fundamental frequency 2 pi over t to be w0. So we can sort of write this in this case. So if we were to write this in this case, right, we can if in the case, so let's write down the spacing again equal 2 pi over t. Yeah, so which is the w0. W0 will be the spacing of it. If my spacing is not zero, so it does make sense that for each one of my k, when I step through each one of my, so the spacing is pretty much my width, the width of my differences, and then the k will be like the index of like, oh, this is the index 1, index 2, and index 3, so on. So when the spacing is not zero, so it doesn't make sense that we can just have a constant w0 and use that k to sort of iterate through and say, okay, this is the first one, this is the second one, this is the third one. But then in a continuous case, when you have the, sorry, it's not continuous case. Let me rephrase that. In a period case, your spectrum now becomes continuous. So yeah, you can see my head sort of gets around, gets a little bit like confused around. Okay, so in a period case, when this is like very, very close to zero, it no longer makes sense to have this index between them, because you have pretty much just like very, 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 very small thing that get very, very close to each other. So in that case, we instead just use the w to be used as our variable. So this is the reason why you have kw and dw instead of k and fundamental frequency sort of idea. So that sort of tells you the differences between, like, for instance, why in some cases is w0 and in some cases is w. And then the other difference is that when we talk about this is like the roots of unity idea. We sort of have this wraps around. And the final thing is probably you have to take care about the axes itself. So just be reminded that, for instance, some of the axes will be, so in that case over here, because here we're sort of summarizing through my whole like Fourier domain to get me my time information, because that's a synthesis equation. So in this case we iterate through k, and in this case we iterate through w. So you just have to be mindful about the axis, because on the right hand side we have, again, summarizing all my overall my time, and in this case remember that the time itself is continuous, so using the dt integral. So but on the right, on the DTFS, again, this is summarizing all my k, but on the right hand side it's summarizing my n, because n is my time information. So just be mindful about the like what's the axes. And yeah, hang on. The last bit is DTFT, and the synthesis equation will be d omega. So yeah, that's pretty much it. And what's the thing here? It's just it's n. Okay, yeah. So just to be mindful about this bit. Yeah, and then with all that information, you can pretty much construct all the things that you require for this, for the CTFS, CTFT, DTFT, and DTFS. The final thing to be mindful about is that you can actually sort of write your duality happening here. So if I just erase all that, so as you can see that there's a clear duality that will be happening right here. Like this looks exactly the same as this, and then this looks exactly the same as this. and another duality happening between this and this, and a duality happening between this and this. And if you just sort of consult, the reason for that is just like discretize a period, continuous, period, yeah, and then a period, continuous, period, discretize. So yeah, that's sort of the reason why the duality comes in. And I think that pretty much summarizes everything. The final remark is that if you go back here and take a look at the Laplace transform, which has your regions of convergence, the regions of convergence, and then you have your Fourier. Sorry, scratch that. I have no idea what I'm talking about. Again, take a look at the left hand side. You have your Laplace transform, and the right hand side you have your zeta transform. Is it zeta transform? Z transform. Yeah. Anyway, not zeta. Something really interesting is sort of struck my mind is that, so in your Laplace transform and your Z transform, why is it that the case that your Fourier, like you know that the Fourier is when you have sigma equals 0, right? So your sort of Fourier sort of resides on your imaginary axis. So when you talk about the regions of convergence about my Fourier transform, you always have to consider about the imaginary axis, right? But on the right hand side, if you have the Z transform, the Fourier, like the Fourier transform, which is the discrete time Fourier transform, actually resides on this units of circle. So why does it make sense that one of my Fourier transforms sits on the imaginary and the other one sits on the unity of circle? Like they're exactly the same thing, but like one of them is sitting on the unity of circle and the other one is on the. So this sort of boils down back to the discussion when we have talking about the roots of unity before. So this is why I'm talking about this. Like because of your discretization results in periodicalization. So you fundamentally have to talk about the idea of roots of unity because of this wraps around effect in your periodicalization. So if you were to like take a look at the whole, like maybe I should use a different color. If you sort of look at like the whole thing here, it'll probably be like this string over here. And then for another periodicity, you will have another here and then another here. But while in my continuous time, there's no wraparound effect like that. So I just have the simply like the same linear structure that goes down. So yeah, just to emphasize again, because in my discrete time periodicity, like the periodicalization of my spectrum, so I really just need to extract one period out to talk about the whole thing, right? I really just need the one periodicity to talk about this, so I have this wraparound effect and talking about roots of unity. And if you change this to a polar coordinate, then you essentially have the r equal 1 to represent your unity, roots of unity. So that's why the structure sort of looks a little bit different, but they are fundamentally the same thing. As again, if you sort of have like a spectrum that resides on the third axis, it will be just wrapped around here, both of them going out of the page. Yeah, so on the left hand side, aperiodic, so no periodicity, so you can run through the whole spectrum from negative infinity to infinity. Right hand side, wraps around effect, so yeah, just one period and talk about like the next one will be repeated. So yeah, that's pretty much summarize everything, and thank you for listening. Yeah, thank you.